Okay. I figured, I'm sorry, I figured I'm supposed to do something. I'm just going to do what you want. I'm just going to log in. So I'm going to share the screen.
So,
Yeah, so I assume tu veux juste ça ou cherche du temps parce que c'est juste que comme tu le mets là, ça tu t'oublies et
you should be all set. So it's
I think, yeah.
to the cloud already.
Okay.
Put the recording. Yeah, I think I was assigned to this, and there was some confusion or something. So it's like yeah, you don't need to be. Are you okay? I need to rise in my. Okay. I'm all good. All set. Cool. Can people see us? No, it's now no one's watching live, right? No, it's just a recording. Do you want to be here? Do you want to sit?
I do wish I can like.
Or maybe you can sit in front. And,
yeah.
Okay. Yeah. Should I start or? Yeah. Ciao. Hi everyone. I'm going to start the tutorial.
Everyone, we're going to start the workshop now. So please direct your attention here.
Cheers. So I'm going to do a quick tutorial of Percival, the software that you'll be using for the Quandela challenge. So Percival is like a linear optical tool to do quantum computation with linear optics. I guess it started because when we started the theory activity in Quandela, of course, we wanted to be able to simulate what we will be running later. And so we wanted to try to do, linear optical computation. And so the first method we tried was to use Xanadu solutions, strawberry fields. But like it's meant for continuous variables, not the kind of photonics we do at Quandela. So it was very inefficient, very slow, and we couldn't, be able to simulate what we wanted precisely. So we thought a bit, and one of our interns that became a PhD afterwards came up with a new way of strongly simulating linear optical circuits. And so you'll see later that we have a backend that is called Sloth, which is exactly the work he did. And so based on that, then people joined effort, and basically we built a software solution for linear optical circuit, which is very nice. I'll show you. And so, I'm doing quantum algorithm at Quandela, but my side activity is to actually organize hackathon back at home in Paris. So we had the second edition of our hackathon last November. But for the first edition, one of the challenge was to actually reproduce a paper I mentioned in the talk earlier from Valeria Sergio, which is about reinforcement learning. And for this tutorial, I thought, okay, what's worst? I mean, it's really natural for me to just solve the challenge for you, so you see the kind of challenge that you could be asked for in the Quandela challenge. So here, typically, what we just do is we pick the paper and we ask the participant to reproduce the paper. So the paper is here for reference. And basically, the idea is to try to explore reinforcement learning and to compare the purely classical strategy where you have a classical channel and you can only send bits of information compared to a quantum channel where the agent in the environment can actually exchange quantum states. It's good to keep that in mind, but you'll see later that it's kind of hard to then map it back to this kind of image, but it is really what we do. And so the idea here is that basically in the quantum channel, roughly, what you can do is some sort of Grover search. So basically you can find a way to implement a Grover algorithm into finding the action that is going to be rewarded the most by the environment. And so this is what roughly what you see here on the first image. So this is a typical reinforcement learning plot where on the x-axis you have the the epochs, which is just the number of runs you're going to do your learning on. And then on the y-axis, you have the cumulative reward or the reward. So here it's just the reward, which tells you how good you are doing the reinforcement learning. And you see an interesting behavior, like quantumly, you see that you learn much faster. So you manage to pick up the right states that you want, to keep doing, and much faster than the classical strategy. But then afterwards, you see that you have a drop and you're actually doing something very weird, and you lose what you've learned before. And basically because you were doing Grover search, and at some points you have some sort of over amplifications. If you think of Grover as some sort of reflecting your states to be closer to the target state, at some point you'll do so much more reflection that you're doing nonsense basically. So this is what happened here. And so basically the paper says, okay, so let's do something a bit better. Let's combine both approach and have a combined strategy, which starts quantumly. And then as soon as you start dropping or over amplifying through Grover search, you switch to the classical strategy. And then you have a learning method that always outperforms a purely classical strategy. And so that's basically what we'll be trying to reproduce here. Okay. So, okay. I just start with importing some package for, sorry. Yeah, a disclaimer. This is not my computer, so I'm going to be very slow on typing and stuff because I don't know the keyboard, a bit lost. But I don't have internet on my computer, so that's a bit sad. Okay, and so basically, I mean, maybe I could show you the paper quickly. Basically, why we picked up this paper for the challenge, the previous challenge, not this one. I'm not solving this one challenge, don't worry. Is that because, like you have this kind of stuff that are easily implementable on Parseval. It's linear optical computation. So here you see that you have two modes, photons going through, beam splitters, phase shifters. This is typically what we use for linear optical computation. This is our components to implement logical gates or quantum gates. And shortly after, you see that you have linear optical, you see, right, at the back, it's big enough, yeah? I assume it's okay. So here you see that you have linear optical circuits. So it's what we really want to do. Dispersible. Hop. Okay. And so basically what you see here is 50-50 beam splitters, which are almost like Hadamard gates. So what I'm going to do is to just define the Hadamard gate. Hadamard, which is just a beam splitter. So Perceval is what I'm using. I'm going to call a beam splitter, BS. And I'm going to use a Hadamard convention. So that's going to be my Hadamard gate. And if I want to display it to show you that I haven't cheated, and this is actually an Hadamard gate, I'm going just to display the unitary with .u, and you see that it's actually an Hadamard gate. The reason why we have so much, so you see that you have .h, you also have .rx. If you look at the library, we have a lot of different definition for the beam splitter. We did that because we wanted to stick to the literature. And in the literature, when you look at a linear optics paper, everyone has his own convention because you can't see the global phase. So basically, you have a freedom of choice when you want to define your beam splitter. So everything is equivalent at the end when you run your computation, but in between, you might have different behaviors when you have different conventions. So that's why we allow for different conventions too. Okay, so we have defined our Hadamard gates. And so when you look at the paper in the appendix, you see that basically what they have as their unitary transformation is this kind of Mach-Zehnder interferometer. So a Mach-Zehnder interferometer is just this beast. It's just a beam splitter, a phase shifter on the upper mode, another beam splitter, 50-50, and then another phase shifter. And what's nice about this kind of optical component is that they can implement any 1 qubit gate. So this can implement any rotations on the box here. So this is usually what's used, but then we have to stick to the convention of the paper just to make sure that we are implementing the same circuits. So they say that the unitaries obtained at the end with the Mach-Zehnder interferometer is this one. But if we stick to the Hadamard convention, what we obtain at the end, if we just apply the Hadamard gate, phase shifter, Hadamard gate, phase shifter, is this unitary, which is almost the same, but you see that you have a global phase that you have to cancel at the end. So basically what we are going to do is we'll be adding 2 phase shifters at the end to cancel the global phase. Something we can do. Okay, so I'm going to add some sort of code. And so I'm going to define Mach-Zehnder interferometer. So the Mach-Zehnder interferometer, in a Perceval circuit, you can give names to your circuits. So I'm going to ask for the functions to provide a name because I'm going to use this Mach-Zehnder interferometer to implement different parts of the circuit. So first I'm going to ask for a name. Then I'm going to ask for angles. So theta, which is the first phase shifter here, then phi, which is the second phase shifter. And then, as I said, I'm going to need a last, 2 last phase shifters with the same phase to cancel the global phase here. So I'm going to ask for another phase here, which will depend on theta. But basically, for now, you can't. I mean, you can define symbolic object with Perceval, but when you define symbolic objects, you can't define in the Perceval parameter, you can define function of other parameters. So that's why you have to define another theta2 that will then be assigned to a function of theta. And then maybe to be a bit clearer, what it's going to output is a Perceval circuit, which is the object that Perceval is constructed. Okay, so what we are going to do, we are going to construct a circuit. So we are going to re-implement this. So this is a Perceval circuit. The Perceval circuit has 2 modes. So we are going to specify the width of the circuits here, 2. And then we are going to give the name of the circuit, which is our first parameter here. Then we are going to add components. So you could add components with double backslash, but here we are just going to use the add method. So in my circuit, I will add a beam splitter. Did I import beam splitter? Yeah, I imported here, so okay. So I'm going to have a first beam splitter, then I'm going to have a phase shifter on the first mode. So the 0 is specifying the mode on which you apply the operation. So here you apply the beam splitter starting from mode 0, because it's a 2-mode transformation, the beam splitter. The phase shifter is a 1-mode transformation. Then I'm going to add another beam splitter. And finally, 2 phase shifters. So the first one is the one from the picture here. And then the second one is to cancel the global phase, as I was saying. So theta2. And then here we need to apply the phase shifter on the first mode as well at the end. So I'm going to put 1 for a change. Up, theta2. And then I'm going to return the circuit. hopefully this works. We'll see later. Okay, and then if you look at the paper, what they have is different type of unitaries that they will use throughout the transformations. So you have the state preparation, UP, which is just going to produce a superposition of the action that the agent can choose. It's given somewhere in the paper. Environment, preparation. Yeah, it just, like you give some weight and then you prepare the actions the agent can perform depending on your weight xi. Then you have the environment that will just perform a reflection. So it's just a swap, which is really easy to do photonically. And here, quantumly, you have the Hadamard gates just to do the conjugate for the Grover search. And then the reflection here for the Grover search. So it's a reflection with respect to the state you prepared at first. So we'll basically implement each bit separately. So one for the environment, one for the state preparation, the Hadamard gates we already did, and then one for the reflection. Okay, so the environment. What we want for the environment is to perform a swap. And because you have a convention in the paper, it's actually a swap, and you put a phase pi additionally on these modes. So basically, we want to implement this matrix transformation. And our MZI implements this transformation. So we have to set theta to -2 pi and phi to 0 to implement the reflection. No, sorry, not the reflection, the swap of the elements. So it's what we're going to do. So the environment is going to be MZI that we are going to call UE for environment, same as the paper. The first element is theta, so it's going to be 2 pi. The second one is phi, is going to be 0. And then we have to remember that theta 2 was a function of these two, and theta 2 was minus pi over 2 minus theta over 2. So we are going to write it. So minus pi over 2 minus theta over 2. So theta is 2 pi, so it's minus pi. Could have written 3 pi over 2, of course. Okay. Okay, so Perceval is doing something weird for the rendering, but basically it's indeed 1 minus 1 minus 1. So diagonal elements are basically 0, and the off diagonal elements up to numerical precision, it's minus 1 minus 1. Maybe you can't see because it's very small. I don't know. You see, or yeah? Let me know if something is yeah, and of course, please interrupt me if something is not clear or you want some precision on some lines. Okay. Then the next step, so we have the environment that does the reflection, then you have the UP that is used for the preparation of the state. So for the preparation of the state, we want to implement this unitary, where you see that if you start from the 0 state, you will have a superposition of cosine on 0 and sine on the state 1. So it's what we're going to do. So if we want to do that, we have to set theta to pi minus 2 xi, and xi would be an external parameter that we'll use afterwards, and phi to 0. So we need to define end goal, right? Because it's going to be a function of xi, basically. So this is to define, sorry, a Perceval parameter. So P is for parameter, basically. So this one is for theta preparation. So I'm going to call that TP, for instance. And then because of this, I also need to define another theta 2, because theta 2 is always a function of theta O. Then I have my triangles. And what I can do is just define a preparation that is going to be MZI, P. The first angle is theta preparation. The second angle is phi, but phi is 0. And then the third angle is theta 2 prep. Okay. So this is for the preparation. And then later, when we'll use this circuit, we're going to set the value of theta preparation and theta 2 preparation to their value, which will be defined by xi, depending on where the reinforcement learning agent is at some epoch, so some epoch will define a value of xi that the agent will choose, basically. And so we'll set that later. And so same fashion, I'm just going to copy paste that, I guess. We're going to define a reflection. So it's a reflection from the initial state. So it basically is this that we want to implement. Action. Nope. Reflection. Okay. And so here instead it's so it's basically the same, but okay. Reflection here. Later on, when we'll set the values of theta 2 and theta for reflection and preparation, we'll have to remember precisely the relationship to xi, which is this value the agent chooses. And so for theta preparation, it's going to be pi minus 2 xi, whereas for the reflection, it's going to be pi minus 4 xi. So we just have to remember that. Okay. And then I guess we are ready to go. So the classical circuit is just going to be that. So it's just a preparation. And then the environment acts with the swap, basically. And the only thing is that then the agent will choose basically the correct probability to put the superposition. And so the probabilities will be given by sine square by this epsilon, basically, which give you this superposition that I mentioned from the paper. So let's go. So the classical circuits will just be a Perceval circuit of, sorry, not two, of 4 modes, right? And I will add on the circuit UP, which I called, I don't remember, prep. And you see that I add prep on the first mode because it's starting on the first mode, yeah? And then I will add on the second mode, the environment here. And I think we are good to go. If you want to display what you're doing in Perceval, we have something called P-display or pretty display. I just learned it today, actually. Marion told me that it was for pretty display. I thought it was for Perceval display somehow. I'm going to display the circuits and I'm going to show you the elements within the circuit with recursive equal true. So here, I mean, okay. Yes, it's more or less what we wanted here. So you have the UP, which is UP here. Of course, we haven't set the right angles for now, but we will. And then you have the environment. So here you see that you have UP, UE. So then we have to set the right stuff. Any questions so far? No one is sleeping. That's okay. Now the more interesting part, the quantum circuits. So basically we'll perform Grover amplification with these circuits. And there is a small trick at the end, which is that you cannot really read out the correct value at the end of the quantum circuit. So what the author do in the paper is that they couple the quantum circuit to a classical round. So basically the classical strategy will learn on this circuit. So each epoch is one of this circuit. And the quantum strategy will learn on this circuit. So it's a combination of quantum and classical circuits. And so basically to be fair in the comparison, one epoch on this counts for two epochs in the classical circuit, just to make a fair comparison, because here it's going through two circuits. Yeah.
Well, it's just having that classical circuit quantum does so much better. Classical learning or
well, really, like the quantum circuit is performing Grover as such. So that's the advantage using the quantum circuit. Does that answer your question or not really? Do you know? Maybe you don't know Grover algorithm. Oh, yeah, okay. I take it for granted, sorry. So Grover algorithm is an algorithm that allows you to look through a list to find a marked element faster than you would do using classical methods. And faster is a square root improvement compared to the complexity. So instead of n squared, for instance, it goes to complexity n. Okay. And the way it does that is basically by it's going to be a very like a oversimplification, but basically think you have two states. So this is basically your target state, the one you want to find at the end. And this is going to be your, if you want, your garbage. So all of the states, they are in this kind of vector. That's why I'm saying it's oversimplification, because you can't represent that. And so what you're going to do is you're going to start with, I don't have more colors. You're going to start with a uniform. You have more color than that? No, I think I have enough space. It's okay. So you're going to start with a uniform superposition of every state, which roughly will give you something very close to the garbage state, because it's a uniform superposition and you have a lot of stuff in the garbage state, right? And so then Grover does some sort of reflection. So basically what you're going to do is you have an algorithm that allows you to first rotate this state to this element, and then you're able to do a reflection from your initial state. So you started from here, and then by doing this transformation and then reflecting back from the initial state, you end up much closer to your target state. And if you do that enough time, you end up on your target state. And the problem I mentioned in the introduction saying you have overamplification, it's because sometimes you end up here, and when you do the next one of Grover search, you end up here, which is far away than you started with. So you have to find the correct number of times you perform Grover search to converge to your target state. Does this make some sense?
yes.
All right. Okay, so let's build this circuit now. So quantum circuits. It's going to be a Perceval circuit. 4 modes. Right. On this, we are going to add the We're going to add the state preparation, which I call prep. We are going to add the two Adamar gates. So Adamar gates on 0. Why does it not know Adamar? Okay. The Adamar gate on mode 2. Then we are going to add the environment. Mm. Then we need to undo the Adamar gate. The Adamar is itself inverse, so we don't need to conjugate it. Up. Up. Right, and then we need to perform the reflection. Was it called reflection? Right. It was called okay. I thought it wasn't understanding it. Okay. And then you need to redo again the environment at the end. So quantum circuit dot add to environment. Again, if you want, I can display it. First of all, quantum circuit. And here I didn't put recursive equal true. I just want to have the, coarse grain description of the circuit. And so you see that this is exactly what's here. So you have UP, the two Adamar gates, the reflection, the two Adamar gates again. Sorry, the swap, the two Adamar gates, the reflection, and then again the environment. Exactly that. Does that make sense? Some sense? Okay. And so now that we have the two circuits, so the classical circuits and the quantum circuits, we are ready to actually do the computation and try to reproduce the result of the paper. So for the results of the paper, of course, you need to define a number of agents because you can't, I mean, reinforcement learning is average over a lot of different realization of this particular strategy. So you need to fix a number of agents, which is going to be 100. We are going to try to learn on 1,000 epochs. It works. I've chosen this number because it works. And then we need to put the starting point for the superposition. And so in the papers, it chooses this. So basically 1% on the winning state and 99% on the losing state. And so epsilon is just a function of this. So this is really the 1% of it. And in the paper also, you see here in the classical case that you have reward or not. So basically, if you click, if you're single photon, so you're going to put a single photon here, and you're going to get a reward. So basically, the environment is going to output 1 whenever you have a click on the force mode. Same in the classical case. So we are going to just code a quick function that is going to take your circuit, run it, and if you get a click on the fourth mode, then you get a reward. So if reward, it's going to take a circuit as inputs, and it's going to output a Boolean or whatever. It could be just an integer. And now if you want to make a simulation in Perceval, you have several ways. One of the ways is to create an object which is called processor. Um, that will basically incorporate all the elements you need. So it will take a circuit, take an input state. If you need, it can take also post-selection schemes, heralding schemes, etc., etc. And basically do the computation or apply a backend on this and output what you want. So you need to precise the backend. So I'm going to use sloth, the thing I was mentioning at first. It's going to take this circuit within the processor. Then I'm going to put an input to this processor. So to put an input, I need to create a state. If you want to create a state with Percival, you have two ways. Either it's a basic state, which is just one instance of a Fox state. So it's really what we want. So here, if you look at the paper, they say that they always put the single photon in the second mode. So this is what we are going to do here. We are putting the single photon in the second mode, only one. And then we are going to call the sampler method because we just want to output one sample when running the circuit. So algorithm. Dot sampler. Yes. So this is the sampler, and then we are going to actually output one sample, or samples, or one sample. That sample. And we are going to ask for a number of sample. So it should be S, I guess. Which is here going to be just one, because we want to run it for one instance. So here, sloth is a bit overkill for it because you're only asking for one sample and you're computing the entire probability distribution at the end, but you could use another backend like Clifford and Clifford, like you have a lot of different backends that you can find on the Percival documentation. And so then what we are going to do is, if the photon is on the force mode, we are going to return true. So sample, sorry, I'm using Mac shortcut, so it doesn't work. Sample, so it's a dictionary, so we are going to ask for the result. In the result, we are going to take first element, and we are going to ask whether the first element, because we only have one element, one output state, we're going to ask if that element is the basic state 0, 0, 0, 0, 1. So if it clicks on the force mode. Okay. I hope I didn't make too many mistakes on the way. And so now we are ready to actually do the classical strategy. So the classical strategy, you're going to have to want to construct a list of reward for the agent, even average on a lot of agents. And so we will be ranging the number of agents. For each agent, we're going to perform basically all the steps for the reinforcement learning procedure. So first, we want to initialize the value set here of epsilon. It's already here. So, okay, maybe I can show you the paper again. You see that basically the priority of functions of sine and cosinus of xi, and then xi, where is it defined? here you see that epsilon is a function of sine square of psi. So if you want to invert this, because we have this value, we have to take the arcsine, basically. So it's what we're going to do. Xi is going to be the arcsine of epsilon, the roots, square root of epsilon. And so we need to define what's epsilon. And so epsilon is just epsilon 0 here. Okay, so that's for the initial value of psi. And then we can set the right angles to the values we wanted. So for the classical circuit, we don't have the reflection, we just have the preparation. So we are going to set the value of this perceivable parameter to the correct one. And if you remember well, what we said was that for the preparation of the state, theta would be pi minus 2 psi. So it's going to be np dot pi minus 2 times psi. And theta 2, if you remember correctly, was minus pi over 2 minus minus what? Minus theta over 2, something like that. Minus theta over 2. Yeah. And so theta is this, so minus theta over 2, so minus plus pi. Yes. Want to be a bit more ergonomic. We could do that. Master me for the code. So, okay, minus one. Okay. Okay, so that's for the initialization. Then we are going to build this array of epsilon, which is just going to be, sorry. It's just going to be your epsilon. And so epsilon is actually something that I haven't talked about yet. So when you do reinforcement learning, you have so an agent talking to an environment, he sends actions, the environment assesses the actions, sends back a reward on these actions. And then the agent has to take, like a new direction or to find how to optimize its behavior. And so it's done through a policy. So a policy is how the agent react to the environment. And so here, basically, the agent is a bit naive. What it's going to do is that if it doesn't receive anything, like no reward, it won't do anything, which is a bit naive. But if it gets a reward, it's going to go a bit more towards the state that has been rewarded. Okay, so now we are going to do the loop for all the epochs. So for each agent, if the agent got a reward, circuits, the agent is going to update his strategy. So to update his strategy, it's going to, like it's defined in the paper in the appendix, it's going to put more weights on the winning states, as I said. So I guess I need to define H1. Up. Right. Okay. So then it's going to give a new weight for epsilon. So epsilon is going to be the same, H1 divided by H0 plus H1, but then H1 has changed, so epsilon is going to give more weights to the winning state. Then Xi is still the arcsine of the square root of epsilon. Epsilon. And then we need to reset the angle as we did before. And so if we add a reward, then we'll store in the array that we actually add a reward. So we are going to store 1. Else we are not going to do anything. So the agent is not going to change its strategy. And so, sorry, array. And so reward is now, yeah, 0. Okay. And then okay, extra. And then we are going to store in eta classical the value of I mean all the epsilon. So basically the reward for each agent, right? Sorry. And then we are going to average what's in eta classical to get an average reward. Does this work? No, I get a get reward here. Ah, it's just reward. I'm going to call that get reward. It seems to run. It hasn't been like minute is a bit broken, but it shouldn't take too long. Yeah, seems good. Okay, so what's happening now is that I'm performing the strategy for a lot of agents. They each try to learn. And if they learn, or I mean, even if not, like I'm going to store it in an array and do that for all agents, right? So that's why it's taking a bit of time. So basically, the number of actions I'm performing is the product of these two. So it's 10 to the 5. And then I'm going to average eta classical for all agents to get an average reward for each epoch. Does this work? Okay, something is not working. What did I do? probably storing that. The wrong place. Right. Ah, good catch. I wanted to take the square root of epsilon and I multiplied it by 0.5. Okay. Okay, so we'll wait a bit and hope that it's the right one now. And we can do actually the same for the quantum strategy, right? So if I want to do the same for the quantum strategy, I won't bother too much and copy paste everything almost. Ah. How does Windows work? Yeah, badly. The quantum strategy, of course, we're going to call it. What? Ah. Um, theta one, theta two. So in the quantum strategy, we have two angles. We have the one for the state preparation and the one for the reflection. For the reflection, it's minus 4 psi. I remember well. So then we can set the value for the preparation and also set the value for reflection. Up. Okay, did it finished? Yeah, let's hope it's correct now. Cool. So basically, we can't see because we need to compare to the quantum version. But the classical strategy looks like this. Okay. And here we have something that roughly resembles what we should have. Um, okay. So now, yeah, the quantum version. Okay, it's working now. As I mentioned, we should take less epochs to make a fair comparison between the two, the classical and the quantum case. So now we are going to get a reward of the quantum circuit instead of the classical circuits. The policy is still going to be the same. So I update my weight only if I win, and I put more weight to the winning state, same as before. So everything is the same. Yeah. I need to update the rate, the correct rate. The only thing is that, as I said, it's a bit weird, but because the fact that we have one epoch compared to two epochs for the quantum version, I'm going to append twice 0.5 instead of only one. But if I lose, I'm also going to append twice 0, right? So now it's a fair comparison to the classical case. And here I should update the right value. Okay, I'm just looking at what could have gone wrong if something goes wrong. Cha, cha, cha. Yeah, we'll see. Any questions so far? Nope. So that resembles what we should obtain. So you see that, I mean, we are going to plot the two at the same time, but here you see that at 100 epochs, we are approximately at 0.2 in terms of reward. And here, okay, bad choice. I should have looked at 50. Okay, so 50, we are at 0.1 around here. And here at 50 epochs, we are at 0.4, which says that, okay, we have indeed managed to implement graph as such, so it's faster. But you see the fact that I mentioned earlier, that you have over-amplification if you wait too long, and then you stop, like everything you've learned, you learn it. So it's a bit of a shame. And so what you can do instead is so basically find the point where you achieve this point. So find the maximum of your growth as such, and then switch to a classical strategy. So I'm not going to type all the code here. It's already typed. Here it should be a ref, I guess. Hop, hop, là. Does this work? Okay. And so hopefully with this last run, we will be able to obtain these plots. So the classical strategy, the quantum strategy, and then the combined strategy. And so this is not something we do now, running the quantum backend. Here we are only just using simulation to reproduce the result of the paper, but of course, I could easily just change the backend, create instead of a processor object, create a remote processor, send it to the cloud. Then if I want on the cloud, I can still do simulations with the right noise model that is suited to our device. Or I could send it directly to the QPU, which is going to do exactly the same, right? I have the same code, but it runs on the QPU. So this works. Okay. And so you see here that we have exactly what we talked about. The fully classical curve, then the fully quantum strategy, and then the best of both worlds when you try to run the two, which is exactly what we had. And so if we had run it with more agents and more just more agents, this is what it would look like. You know, it would be less scattered. It could be much better like this. So I guess this is all I wanted to say for this tutorial. Do you have any question? Yeah.
I heard you tell out people, right? But the bigger test, what happens if you switch back or something that wants you to the higher level?
Yeah. Yes. So, what question? It's like, you want to collect some. Thank our speaker for not.
Yeah, I'm here if you have.
Talk, which is, I believe, a career panel.
Yes.